So the work I'm going to present today is in collaboration with Yusheng Wang from University of Illinois and Jipeng Bao at Carnegie Mellon. So what I'm going to talk about today is some issues in robust perception for robotics. The kind of thing that we would like to do in perception, the kind of thing that's illustrated on this video, basically scene interpretation, detecting objects, and so forth. The way this is typically done is to have a lot of training data, large amounts of training data, to train a model and then make decisions based on that model. So what I would like to explore is a couple of key limitations to make those systems robust. The first one is that we are typically limited training data. This is a major emphasis of research currently, things like self-supervised learning of those models or one-shot learning and so forth. So this is one of the key limitations that we need to address. A second limitation is, even though in the previous video I showed you one particular task, detecting objects, in reality, what we want to do are many different tasks at the same time on a given observation. For example, segmenting the scene, estimating depth, perhaps estimating normals, answering questions about the scene, perhaps. In other words, we need to be able to perform multiple visual tasks on a given input. And so it's very inefficient to train those different tasks separately. We need to find a way to combine those multiple tasks into a single ensemble of learning approaches. This is, of course, a major emphasis of current research. And the idea is to say, well, maybe I can learn an internal representation that is common to all of those perceptual tasks, so that I can do a much more robust and efficient learning of those models, including from limited data. So those are basically the two issues that we're trying to address. One is being able to learn from limited data for perceptual models, and the second one is to be able to take advantage of multiple tasks that we want to achieve on the data in the learning process. So that's what I'm going to talk to you about today, and basically show you a couple of directions that we've been looking at. This is a work in progress illustrating some of the ideas in this area. So the first idea is to share knowledge across multiple tasks and see how we can use that shared knowledge across multiple tasks to improve the learning of those models and make them more robust and perhaps also feasible with more limited data. This is, of course, something that has been explored extensively in the literature. This is a picture from a famous paper from Zamir et al. On taskonomy, which basically looks at, given an input scene, being able to perform a number of perceptual tasks on that input set simultaneously. So that's what we're going to try to address, the kind of issues that we're going to try to address. So let me start with one simple or relatively simple example of this. Let's say that we have an input image like this. This is not a very robotics relevant example, but still an image input. We can do a couple of things with this image. We can either use it to do recognition, basically being able to recognize these objects in different images, in other input images, or we can use it to generate this object from different views, basically synthesized images or hallucinate images. So those are two different two different tasks, two different visual tasks. One is recognition, the other one is image generation. So the question is, given those two tasks, can we design a system so that they help each other in a way that makes the resulting system more robust and in a way that reduces the amount of data that is needed to train the system? So again, this is the idea here. We have a single image or a small set of images as input. We can do two things with them. One is view synthesis, generating new views of the object. The other thing that we can do is to do recognition, recognizing the object that was in input images in new inputs. The question is, can we have both of them helping each other? In other words, can we use the images that are generated by view synthesis to help in training the recognition? Can we use the recognition model to help in generating the new images? And if we can have them help each other, can that improve performance? Can that make the system more robust? So that's what the kind of thing that we explore. So this is the high-level diagram here. We have basically two modules. One is a view synthesis module that's going to take the input data, generate new views of that data. Those are synthetic views. And a recognition module, which simply is going to take as input the input image and generate the label. And then we want to connect the two. One direction is going to be for the view synthesis module to provide images, basically new hallucinated images, if you will, to train the recognition module. So in principle, there is now more data to train that recognition module. But of course, those images have to be correct, reasonably correct for them to be helpful. Otherwise, they're not going to help the training of the recognition module. So we need another connection from kind of a bow tie kind of structure to this architecture, which basically links the recognition module somehow to the view synthesis module to render the view synthesis module more accurate. And if we train this together, then in principle, we can have those two tasks helping each other and reducing the amount of data that is needed to train the system. This is a more detailed view of the same architecture. The top one is the view synthesis part. The bottom part is the recognition part. The view synthesis module basically takes an input, which is a feature vector and a noise augmented with a noise vector, transforms it with an arbitrary transformation, and then deconvolves it into a generated image. This is based on an architecture called Hologram that was introduced earlier in the references at the bottom. The key difference here is that architecture is modified to take into as input the output of the recognition module at the bottom, so that the two can be tied together. The recognition module in this case is based on FBNet, which is another standard architecture. So the point is that now we have those two combined. The view synthesis modules helps by generating additional view. The recognition modules help by generating an internal representation of the class in input to help generate a correct new views. So that's basically the idea of connecting those two tasks and seeing how they can help each other. If we look at performance improvement, this is an experiment here on a difficult task, a one-shot recognition, fine-grained recognition, so 50 classes. The orange shows the performance of that network, bow-tie network, and blue shows a standard baseline, and same thing on a car data set. So this shows the improvement in performance using this simple idea of combining the generation of new data and the actual task of recognition. So that's encouraging. And we can look now at generalizing this now to multiple tasks. So again, the idea here is that we have an input image, input data from vision, and we want to generate multiple outputs, things like semantic segmentation, depth estimation, etc. The question is, how can we do that effectively? The current state of the art looks at basically training a multitask model that will try to integrate all those tasks in a single model. What we propose to do is, inspired by the previous example, is to insert here a generative model that will now generate new example together with the multitask modeling, with the hope that just like in the previous example, it will facilitate the flow of models and knowledge across the task, and it will ultimately help having all those tasks interact with each other, and also help training the system with reduced amount of data. And I will show you some examples of that as we go. So how can we do this? Well, a naive approach would be to simply say, well, I'm going to build a generator, just like in my previous example, that's going to generate not just images, but it's also going to generate annotation. So for example, if I'm interested in segmentation and depth, I'm going to say, well, my generator is now going to generate images and those pixel level annotation. So that's nice. That should work, right? I should be able to use the same kind of architecture, the same kind of idea that I had before, except that that doesn't work. And the reason why that cannot work is because I cannot, in practice, generate those pixel level annotation. For example, segmentation labels or depth labels. So I cannot do this directly. So what can I do instead? All I can do is to generate the images, and I can do this only approximately. So what can I do? Well, there are two approaches that I can consider. The first one is what is called self-supervision. One example of that is a system called SimClear from Chen et al. In ICML 20, which basically says, I'm going to generate new views, and I'm going to do it in a way that will enforce consistency of the internal representation of those views for each input image. So given an input image, I can generate a number of different views, and all of them must be consistent in terms of their internal representation. So it's entirely self-supervised in the sense that the criterion that is used to train the system is the consistency of the internal representation. If we use this with a standard technique for a given task, in this case the segmentation task, we can see an improvement in performance, meaning that by generating new views, inserting them in the system and using them to train the system, we have an increase in performance in a way that is entirely self-supervised, meaning there's no need for additional labeled example. So that's good. That's one idea that can work. A second idea that is promising is to say, well, I don't have pixel level annotation, but I can have weak annotation. For example, the type of the scene, in this case, a bedroom. Okay, so maybe I can use this to guide the training of those generating images. So this is how this works. We have again a network that is going to generate those images, and this time, instead of having this self consistency, I'm going to use an auxiliary task, in this case scene classification, to refine the network. Okay, and I can do this because it's easy to have those high-level labels, for example, the scene class, unlike the pixel level labels, which are difficult to get. So you can, again, test that with an existing task and an existing system and see that if we do that, we have an increase in performance. So in other words, this gives us two ways of controlling the system, if you will. One is the self-consistency of representation, and the second one is a downstream task, for example, self-scene classification. So given that, this is the system that one can build. We have an input image, in a generative network that is going to generate new images based on that input image. And this is going to be controlled by two different criteria, if you will. One is self-supervision, as I mentioned earlier, that is the generated images must be consistent in their internal representation. And the second one is the multitask network that must generate representation that work well for that refinement task. Okay, let's look at this architecture in more detail. So at the bottom, we have an image generation system, which is based on existing GAN type of system that's going to generate images that are used as augmentation for training the multitask network, okay, which has as output the various tasks that we want. So segmentation, depth estimation, surface normals, and so forth. In addition, the self-supervision network is going to ensure that the representation, the internal representation for those images are consistent. Now, the key here is that on the right, we have this additional refinement network that is going to feed the output of the multitask network to a classifier that's going to evaluate those representations, those outputs on this auxiliary task of scene classification. Now, the important thing here is that for those images that are generated images, the performance of the network, the loss of the network is evaluated on this last piece, so that there is never any need for pixel level and for the pixel level annotations directly. Okay, that is basically the key to this, to use that auxiliary task to be able to refine the network on those generated images. And again, that bow tie structure that basically ties the task network with the generated images network. If we do this, we can get to those kind of results. Those are results on 3 different tasks simultaneously: semantic segmentation, depth estimation, and surface normal prediction. Importantly, this is compared with results on state-of-the-art techniques using only 25% of the data that was normally used to train those systems. So that it has the advantage that both we can combine those tasks and tie those tasks better, the multitask better, but also we can reduce the data that is needed to train those systems. Those are qualitative example here. This is the top row is single task, so doing each of those tasks independently. The middle row is multitask together. And the third row is using the network that I presented, the architecture that I presented. Okay, this is using this time 50% of the data. So that gives you a qualitative view of what happens when we use that shared knowledge between tasks in this architecture. All right, so that was the idea of using multiple tasks and sharing knowledge across multiple tasks using a generator. The second idea that we're exploring is the idea of leveraging what I call leveraging implicit scene representation. And the idea here is inspired by state-of-the-art work in what is called NERF, which basically says that if I have some images of a scene, I can build a internal representation of that scene so that I can generate now images from other views of that scene, essentially. So given array parameterized by 5 parameters, x, y, z, theta, phi, I can generate the RGB and occupancy image at any point in space. Any point in space, x, y, z. So this is now a standard approach. The question is, can we do this now in a multitask way as well? In other words, instead of just generating RGB, can we now modify the architecture and extend the architecture in a way a little bit similar to what I said earlier, so that we can perform other tasks such as segmentation, etc., to be able to do this in a robust fashion using that representation. So this is the general idea here. We start with the target scene. The input is a viewing ray and a position. We divide the properties that we want to extract for our different tasks into view-dependent properties, for example, shading and color, and other properties that are not view-dependent, orientation dependent, for example, semantic labels. So those go into two different networks that will generate those two properties for each ray, basically similar to the original architecture, but this time using multiple tasks at once. The training requires, of course, some input for those tasks, and that we get from pre-trained individual single task models for each of those tasks. So this is an example here of what we get. The RGB that is generated is the same as the RGB that is generated from the original approach, of course. But then in addition, now we're able to train the network to generate the other outputs as well, meaning to be able to do the other perception task. So what can we do with this? Well, one thing that we can do is to use now that data that is generated using that representation as new training data for those tasks. And this shows the example of performance improvement by doing this. So this is taking an existing system, TaskNet, and to retrain it now, refine it using the images, the data generated by our system, as I showed in the video earlier. So this goes to trying to reduce the amount of data by basically generating a new way of generating new data. This is a visualization of the type of result that we get now if we use, again, that representation, that approach on new data that was not seen before. So this is what I call the after refinement versus the before refinement, which is using a standard single task network on that data directly. And you can see the improvement in this case in the reshading and the surface normal estimation. Yeah. So those are the few projects that I wanted to talk about today, just to give you a sense of some of the things that we can look at in terms of using shared knowledge across tasks. The idea of using generative networks to help reduce the amount of data and tie together those multitasks, and new ideas in leveraging current work on implicit scene representations to do this kind of thing. Thank you.